Good evening. So, guess you can hear me. Um, my name is Charisoulis, and I represent Lehigh University. Um, I am from Display Research Lab, and this is my team: Nack-Bong, Choi, Abbas, Jamshidi-Roudbari, and my supervisor, Professor Hatalis. And today I'm going to present to you our work with NASA Ames Research Center in collaboration with Dr. Yijiang and Jing. And I'm going to talk about carbon nanotube sensor arrays with PIN diodes. So previous work done by Dr. Lee's and Dr. Lu's group, they have demonstrated this this inter-digitated electrodes that actually, when you deposit carbon nanotubes on top of them, they actually are sorted, and then you can observe some current flow through it. So actually, some of their previous data that they have published before is, as you can see, those three groups, this is a graph with IV curves, the voltage versus the current response. And the first group has three droplets of 0.05 microliters of carbon nanotube solution, and it's the most conductive one. And then the second group has actually two droplets, and the third one has one. And they've measured the third one because it's not as responsive as the other ones. So some of their data as well are presented here, where the carbon nanotubes change their internal resistance when exposed to different concentration of gases. So not only you observe the baseline resistance, as you can see here, that they have this resistivity for the different concentrations of carbon nanotubes deposited on top of the inter-digitated electrodes, but they also change the current flowing through them. And so the current flowing through them is always analogous to the gas concentration and the material properties of the carbon nanotube sensors. And as you can see here on the left side, we have single wall carbon nanotube sensors with two different coatings. And actually, as you can see, not the same two. You can observe different concentration of different gases with different responses. So both of these graphs actually are the response in milliamps versus the gas concentrations that you're able to observe with those sensors. And for the right hand side also, we have single wall carbon nanotube sensors without any coating. So actually you can see that they have very different response, those two sensors. So I want to draw your attention to those to chlorine and ammonia, that we were also include that these two materials are the ones that we also used for our experiments, as I will present later. So all of these previous measurements were done with single pixel on single sensor platforms, meaning that these measurements were taken through only one pixel that had only one interdigitated electrode. So actually, in order for somebody to take many measurements out of those pixels, they have to have a lot of pixels, which increases the cluttering of the wires. So in this presentation, we're going to have a novel way of implementing the above sensors on arrays, utilizing diodes and transistors for addressing the individual pixels in order to reduce the wire cluttering. So now I'm gonna present some data that we have from some of our previous devices, and I wanna also point out that these diodes are not the sensing element. Actually, only the interdigitated electrodes are the sensing elements. The diodes were passivated, and only the electrodes that the carbon nanotubes were deposited on were exposed to the gases making the measurements. So the diodes are only there as sensing elements, as addressing elements. So these diodes are low liquids and they have low series resistance. And such devices are like these PIN diodes that we have fabricated on LTPS, low temperature polysilicon technologies, on SOI and on glass substrates. And this is one typical such device measured in our lab. And the series resistance of that diode is to the order of 100 ohms, and the area of that diode is 224 square micrometers. And the leakage current, as you can see here, is around the 10 nanoamp level, which is adequately small, because some of these diodes are going to be forward biased when we're going to be addressing specific pixels, but some of the other diodes that they're not used for addressing at that time, they're going to be reverse biased, and the current has to be very, very low level in order not to interfere with the measurement. And as well, the on resistance has to be below the delta R sensitivity of the sensor that we are going to be using for that measurement, in order not to interfere again with our measurement, so we can minimize the systematic error for our with our setup. So a multi-channel measurement requires many similar sensors to be placed next to each other, as I said before. So as you can see here, the resistance, each individual resistor is one interdigitated electrode element in our design. And as you can see, the resistors are the only thing that is exposed to through the carbon nanotubes to the gases, and it's changing its properties according to the gas concentrations, those diodes are only to read out. So the way this schematic works is we actually force a current through individually any of those rows every time. So if you want to have to scan the entire array, you either force a current in parallel, or as I will explain later, we have some other approaches that you can scan its individual pixel and make the measurement one by one. And then by connecting every column, each one column at a time, to ground or to low potential, the current has a path to flow through the pixel that we are trying to address at that time. And by measuring the voltage at that node, if this is grounded, for example, or this is grounded, we're trying to measure that pixel. That's how we obtain the resistance of the actual sensor. And that's how we can also obtain the change in resistance when it's going to be exposed in various gases and vapors. So various active architectures for addressing the 8x8 arrays and the 16x16 arrays of sensors were invented in our lab. So this is based also on some of our previous work. And I'm going to present to you three of the approaches that we use for this active gas sensor implementation. So the first approach is we fabricated only the inter-digitated electrodes in series with the diodes, and then externally these switches with the Y line high and the X line low are going to be connected through the multiplexing and demultiplexing, and we're going to force current through Y line and X line in order to be able to acquire the measurement. Then these are only simple 8x8 arrays, and as you can imagine now, as you can see, using that approach, the wires that we have are 16 wires in total in order to address these individual arrays, whereas if you had 64 sensors before and you have two wires per pixel, that gives you immediately 128 wires, which is a huge wire cluttering problem. Then a similar approach was used for a 16x16 array. So this individual pixel here represents actually 8x8 arrays of sensors, and I will present the schematic in a little bit. And actually only PMOS and NMOS transistors were integrated with those arrays, and those PMOS and NMOS transistors have different terminals at the gates for Y switch A and Y switch B and X switch A and X switch B, where you can apply voltages to those switches and isolate one 8x8 array out of the four 8x8 arrays that make up the 16x16 sensor array. And X line low and Y line high actually were included externally with the switches. So the scheme of driving that approach is pretty similar to the previous one that we have used in our lab to measure the simple 8x8 arrays. And then at the end, I'm going to present a fully integrated 16x16 array pixel architecture where these logic gates are internal to the circuit, as well as those inverters, as well as the Y line high, X line low, and current line. And actually, the only thing that is connected external to the entire setup is a SMU, which stands for source measure unit, where one can actually force a current and measure the actual voltage while the current is forced into a specific node. And we use those SMUs only to acquire the data. So to present to you, this is one of the schematics, and I will show you the fabricated result at the end. These resistors, as I mentioned earlier, are all individual sensors, and the diodes are only for the readout of the circuit. So the circuit works as follows. First, one of the switches is closed, and making one of the rows accessible to the external SMU that I will present later, and then followed by one of the Y switches that is going to be closed, providing a path to ground for the current to flow through. Then the current is applied through the external SMU, so the current is flowing through that resistor, through that diode to ground, and by measuring the voltage at that node, we can actually extract the resistance of this individual pixel there, along with the series resistance of the diode, of course. Now, for the 16x16 array, this is the simplest design. So actually, in order for this to operate, as I said before, we're going to choose one of the columns. I'm sorry about that. And by setting the Y switch A, which is a switch, into a very low potential, we are biasing the PMOS to operate in the on region. And then again, by keeping that Y switch B to high potential, so this entire clutter of transistors is off. And then by forcing X switch A to be at high potential, these NMOS transistors are on. And then by forcing X switch B to be at low potential, these transistors are off. So actually now we can address the entire 8x8 array. and having a driving scheme similar to the previous one, where here external multiplexing switches and they are going to be connected, and then a current source SMU is going to be applied here, and then it's going to be collected there. So by measuring the voltage, the current is going to be collected there. These all have to be grounded. So by measuring the voltage at all of these nodes, individually addressing one of these pixels at a time externally, we are able to measure the resistance of these pixels. So that's how we can address a very simple 16 by 16 array. And now I'm going to present and explain to you how the fully integrated array is working. The way that this works is, again, as I said before, in the current line we apply the external SMU. So that SMU will force the current to measure the voltage at that node. Then what happens next is that we are going to connect the Y line high to the positive power supply, which is also the positive power supply for those logic circuits there. And actually you can see those inverters actually are connected to the positive power supply. And then we set the line low and the X line low to be at low potential, which is also the same voltage for those logic circuits. We have the option of connecting them in a different voltage if we want to, in case something is not working right. And at the end, we're going to apply a binary counter to all those inputs in order to select one logic gate at a time. So as you can see, the ends of the NAND gate are now connecting the same wires and the same here. So this is a multiplexing and this is the multiplexer. So actually what happens is, when the binary counter is giving some input bits, one of the gates is selected. By assuming that this NAND gate gets selected, it outputs a logic 0 to that inverter. And by outputting a logic 0, the PMOS side is enabled. That transistor is on. So the current will be forced through that transistor. And again, immediately, since the binary counter works for them, one gate is going to be selected. For example, this one is going to force a logic 1 biasing the NMOS into the on region. Thus, a path to ground is created. Now, since the current is supplied by the SMU flows through that path to ground, we can actually, by measuring the voltage at current line, extract the resistance value. So this has a little bit less sensitivity, as you can imagine, because we have 3 active elements, the diode and the 2 transistors connected in series, and actually the PMOS, as always, have lower mobility, so that creates higher series resistance and other issues. But still, this setup works, as I will present to you some data later. And now here you can see, thank you. Now here you can see this is one of the SOI fabricated. All of these are the 16 by 16 arrays, and these are the smaller 8 by 8 arrays. And these are all the test arrays that we have included around the wafer in order for process verification. And these are some of the devices that we fabricated on SOI, and these are some of the devices that we have fabricated on glass. For glass, we use quartz, in case you're wondering. And then this is our setup. We have the probe card. This probe card was used to probe the 8 by 8, the small 8 by 8 arrays, because they have 16 wires in total, or the 16 by 16 arrays as well. And this is actually the active circuitry. I'm sorry, the image is not very good. And then, in order to measure them, one of the pixels in each row had test resistors connected in series with the diodes by passing the inter-digitated electrodes. As you can see here, these red ones are the ones that have connected the resistors in series. That's because this is how we measure. Actually, we acquire the resistance value of the resistors that we have fabricated ourselves in order to make sure the setup is working. And then we cover the entire arrays, 8 by 8 arrays, by a P.PSS solution that is conductive. And we did the same thing in order to verify that our arrays were operational by coding them. Initially, we measured the 16 by 16 arrays without any P.PSS solution, and then we covered them with the P.PSS, and we were able to measure the baseline resistance. And then NASA, this is the part from NASA actually. What they did actually is they deposited carbon nanotube solutions on top of our entire sensor arrays, and then they were able to extract measurements, especially with time. And as you can see here, are the bunch of lines that you see are all the lines connected to, are the multi-channel sensor platforms. So actually, each individual line of those is a single sensor. By averaging them, we're able to have very accurate results, more accurately than before. And we were able to measure concentrations of chlorine, as you can see here, and ammonia and chlorine down to 2 parts per million. And to conclude, we have created a novel sensor array and method for a measurement with carbon nanotubes, including PIN sensors. The novel method facilitates the implementation of the multiple sensors in small area to increase the accuracy And the multiple channel platforms were fabricated and tested on SOI and glass substrates. And the ability to measure various gases and vapors with a concentration of 2 parts per million was demonstrated here. So thank you very much for your time.